Have you ever wondered if you actually weigh less at midnight than you do at noon? This seemingly absurd question touches on a fascinating aspect of physics that most people never consider. The gravitational pull from our Sun, though relatively weak compared to Earth's gravity, does create measurable variations in your apparent weight throughout the day. While the difference is incredibly small, scientific instruments can detect these subtle changes that occur as Earth rotates and your position relative to the Sun shifts. The Sun's gravitational influence on objects at Earth's surface follows Newton's law of universal gravitation, creating a force approximately 0.0006% of Earth's gravitational pull. When you're positioned on the side of Earth facing the Sun, you experience a slight reduction in weight because the Sun's gravity pulls you away from Earth's center. Conversely, when you're on the nighttime side of Earth, the Sun's gravity adds to Earth's pull, making you marginally heavier. This phenomenon occurs because gravitational forces from multiple massive objects combine vectorially. The concept of multiple gravitational influences was first mathematically described by Newton in his Principia Mathematica in 1687, though he couldn't measure such minute variations with the instruments of his era. French physicist Roland von Eötvös later developed ultra-sensitive torsion balances in the late 1800s that could detect gravitational anomalies far smaller than the Sun's influence. These historical developments laid the groundwork for understanding how celestial bodies affect terrestrial measurements. Modern gravimeters can measure variations as small as 1 part in a billion, easily detecting the Sun's gravitational effect on Earth-bound objects. The actual weight difference for a 70-kilogram person amounts to approximately 0.4 grams between day and night, roughly equivalent to the weight of a paperclip. While imperceptible to ordinary bathroom scales, this variation is significant enough to affect precision scientific measurements, and must be accounted for in certain experimental conditions. The Sun's gravitational influence creates measurable tidal effects on Earth itself, causing the planet to deform by several centimeters. These solar tides, while weaker than lunar tides, demonstrate that the Sun's gravity affects all matter on Earth's surface. The solid Earth actually rises and falls by about 20 centimeters due to solar gravitational forces, though this movement is generally imperceptible to human observation. Interestingly, the Moon's gravitational effect on your weight is approximately 2.2 times stronger than the Sun's, despite being much smaller, due to its significantly closer proximity to Earth. Jupiter, when at its closest approach to Earth, exerts about 1/10 the gravitational influence of the Sun on terrestrial objects. These multiple gravitational influences combine to create complex variations in apparent weight that change throughout the day, month, and year. Space agencies and research institutions routinely account for solar gravitational effects when conducting precise measurements or calibrating sensitive instruments. The European Space Agency's gravity field missions have mapped these variations across Earth's surface with unprecedented accuracy. Geophysicists studying Earth's internal structure must filter out solar gravitational signals from their data to isolate the geological features they're investigating. Einstein's theory of general relativity predicted that massive accelerating objects would create ripples in spacetime called gravitational waves. The recent detection of these waves by LIGO demonstrates that our understanding of gravitational forces continues to evolve. While Einstein's theories don't significantly change the calculation of solar gravitational effects on personal weight, they provide the theoretical framework for understanding gravity's true nature as curved spacetime rather than a simple attractive force. Astronauts aboard the International Space Station experience a unique gravitational environment where solar gravitational effects become more pronounced relative to Earth's influence. In the microgravity environment of orbit, the Sun's gravitational gradient across a spacecraft can create measurable accelerations that affect experiments and spacecraft orientation. This demonstrates how gravitational effects that are nearly negligible on Earth's surface become significant in different reference frames. While your bathroom scale will never register the Sun's gravitational influence on your morning weigh-in, this phenomenon illustrates the interconnected nature of our solar system and the precision of modern physics. The next time you step on a scale, remember that you're experiencing the combined gravitational effects of Earth, Sun, Moon, and even distant planets. Though the variations amount to less than a gram for most people, they represent a tangible connection to the cosmic forces that govern our universe and demonstrate that even the most mundane activities involve fascinating physics principles.
Thank you for watching. Please like and subscribe.